Hello students, I am going to take lecture on the fluid mechanics today. In this video, I will discuss only about the concept of the pressure. Before that, we will discuss the basic property of the fluid. What is the basic property of the fluid? The definite volume but no definite shape. The basic property of fluid is definite volume but no definite shape. Means same volume can acquire different type of shapes. One more property of the fluid is in fluids they don't support the shear stress. The concept of pressure. What is the pressure? Pressure is nothing but it is the force per unit area. Normal force. As we already know, in fluids there is only normal force, no tangential component. So normal force per unit area is the pressure. Suppose there is a container filled with a liquid and piston is kept on the surface of the liquid and a force is applied on, external force applied on this. So due to this external force, some internal forces will be developed in the static fluid and this will be normal to the boundary surfaces. First of all, we consider a hypothetical surface, suppose cubical blocks. We have shown here. On the cubical blocks, there are internal forces acting on the surface edge that all are perpendicular. Suppose in the same situation, we have applied the force F here also. Suppose we are taking a spherical hypothetical boundary volume, Fi denoting the normal force to the surface, normal internal forces. The above fact indicates that in fluids, in the state of equilibrium, there can only appear normal internal forces. And these forces always has a tendency to compress the bounded volume in the fluid. That is why in fluid mechanics we talk about the pressure and not about the vector forces. This pressure in the fluid is the compressive forces acting per unit area of the hypothetical surface and always normal to the surfaces. Means you can take any type of the surface or cubical or spherical. The internal forces will act on this will be normal to the surface. Only perpendicular forces are working and the perpendicular forces per unit area is called the pressure. Here what will be the, if suppose the cross section area is A, then what will be the pressure on the bottom of the container? Perpendicular force is working here F. So here pressure will be on this point, suppose Q, pressure on Q will be equal to force, perpendicular force upon cross section area A. That pressure only will transmit it to here. And suppose there is a height h, then we can calculate the pressure on the point P. We will discuss this situation below. Pressure distribution in a static fluid. Consider the container shown in the figure. The cross-sectional area A and the height is h. Density is rho. That the density of the liquid is rho, that is filled in the container. The weight of the liquid exerts the force on the bottom of the container. Here the only force acting on the bottom of the container is the weight of the liquid filled in the container. What will be the weight of the liquid? Mass into G, m into G is the gravitational force. What will the mass? Volume into density. Then we can calculate volume. Volume is the cross-sectional area into height. So mass will be cross-section area into height into density. So force on the bottom of the container will be m into G. Means A rho h G. Now what will be the pressure? P is equal to force upon cross-sectional area. A and A will be cancelled out and that will come to rho GH. Here we are ignoring the atmospheric pressure, that we will discuss later. Here we are assuming a system that is out of atmospheric pressure, means here atmospheric pressure is not working. Suppose here P pressure only depends upon the density of the liquid and the depth of the liquid and not the shape and cross-sectional area of the container. But here we have to note that total force on the bottom surface due to the liquid is greater at the bottom of the larger container. We will see here. Suppose we have taken two containers. One container has the larger cross-section area, another container has a smaller cross-section area. The same liquid of density rho is filled with the same height. Here pressure in the first container will be rho GH, as we have calculated above, and pressure on the bottom of the smaller size cross-sectional area container is also rho GH, because it's not depend upon the cross-sectional area. But force F1 is rho, F1 is P1 into A1, that will be rho GH A1, and force F2 on this bottom will be P2 into A2 is equal to rho GH A2. Here A1 is greater than A2, means F1 is greater than F2, means force on the larger container's bottom will be greater, but pressure on the bottom of the both containers will be same. Consider the another example. I have created the situation in which I have made the funnel like this shape. and in this the funnel is straight, but the height from the point of reference is same of the liquid filled in the funnel. Hence F at the bottom, F is equal to pressure at the bottom into cross sectional area, rho GH into A in both the situation, because pressure will be same on the bottom of the both the containers. It only depend upon the height and not upon the shape and size of the funnel and whatever the liquid is contained in this funnel and the vessel. We can observe that the cross section area is same in the both situation. F at the bottom and pressure at the bottom only depend upon the height up to the force to top depends on the height up to the force, depends on the height up to the free top surface of the liquid, no matter whatever be the amount of liquid present and whatever be the shape of the container outside. Now we have studied the container pressure when it was in rest. Suppose the container filled with the liquid of density rho with height h is moving with a constant acceleration a upward in the gravitational field. I have mentioned here in gravitational field means we cannot neglect here the gravitational acceleration. Pressure on the bottom will be P1 is equal to rho G effective into H. Here what will be the G effective? If container is moving upward, the pseudo force on the liquid will work on the downward direction. So the effective acceleration will be A plus G. Hence P1 will be rho H A plus G. If moving downward with acceleration A, same acceleration, then what will be the P2? Rho G effective into H. Here the G effective will be gravitational acceleration minus acceleration of the container, because this is moving in the same direction of the gravitational acceleration, gravitational field. So pseudo force will act on the liquid upward direction. So effective acceleration will be G minus A. Here we have seen that pressure on the container, bottom of the container of the upward moving container. Here we can see that the P1 is greater than P2. That pressure on the bottom of the container that is moving upward with acceleration A is greater than the container that is moving downward. Generate a question here that there is given a container A, there is a container that is moving upward with acceleration A and another container moving downward with the same acceleration A with the same liquid filled in these containers of density rho, cross section area A and height h. Then what will be the difference of the pressure of their bottoms? So P1 minus P2 we can calculate here. That will be P1 minus P2 is equal to rho H into 2A. A plus G minus G plus A. That will be 2A. Now we can calculate the force on the side wall of a vessel. Here we are assuming that container is closed. So here atmospheric pressure will not be accountable. That we will discuss next. Force on the side wall not be directly determined because height is varying. So pressure is different at different height. Suppose there is a point, 3 point on the same horizontal level A, B, C. The pressure on the horizontal level will be same, but pressure varies vertically. So pressure is different, hence we can calculate the total force by the integration method. Suppose a small strip we are taking at a distance x from the surface of the liquid. Dx is the width of the strip. So area will be, cross-sectional area of this strip will be width b into height dx, b into dx, and pressure on this level x will be x rho g. So pressure into cross-sectional area is the elemental force, means force acting on this elemental strip. So total force on the side wall of length b will be, integrating this df from 0 to h, x is varying from 0 to h. So 0 to h, x rho g b dx is equal to half rho g h square b. We will calculate integration here. So it is constant come outright. The integration of x ds will be x square upon 2. I will put here, that will be h square upon 2. So half rho g h square b. Similarly, we can calculate the force on the side wall of length a. That will depend upon length a, half rho g h square a. Here fb is the half rho g h square b, depends only on the length of b. So this will depends on the length of a. Here a is greater than b, so the fa will be greater than fb, means the larger side wall will have the larger force. Here we can also see that force is directly proportional to h square. Average pressure on the side wall, we can calculate the average pressure on the side wall. The absolute pressure of the side wall cannot be calculated because different height have the different pressure. So average pressure can be calculated by total force on the side wall upon area of the side wall, that is F upon BH, half rho GH. Means average pressure is not depending upon the length of the side wall, and it shows that average pressure on the side wall is half of the net pressure at the bottom of the vessel. Net pressure on the bottom of the vessel is rho GH. So average pressure is the half of the pressure. Average pressure on the side wall is half of the pressure on the bottom of the vessel. We can also calculate the torque. Suppose we are calculating torque about the side wall B. So torque will be about this edge. The elemental torque d tau will be equal to df into this distance, this height. Total height is h, that is x, then that will be h minus x. So d tau will be df into h minus x. We will integrate this from length. X will be 0 to h, x rho g b dx h minus x. We will calculate this integration. We will find it 1/6 rho g h q b. Here tau is directly proportional to, torque is directly proportional to hq. Atmospheric pressure and effect of atmospheric pressure on the system. Now we will consider the atmospheric pressure. What is the atmospheric pressure? It is the pressure of the Earth's atmosphere. It is generally taken at the sea level. Normal atmospheric pressure at sea level is 1 atmosphere. That is equal to 1.013 into 10 to the power 5 Pascal. That the unit of the pressure, that is also the Newton per meter square. Fluid force acts perpendicular to any surface in the fluid, no matter how that surface is oriented. Hence, pressure has no intrinsic direction of its own, means it is a scalar quantity. The excess pressure above the atmospheric pressure is called the gauge pressure, and total pressure is called the absolute pressure. Here we can understand this concept. Suppose this container has the cross-section area A, liquid filled with the density rho at the height till the height h. There is a 2 point A and B. Now consider the figure. The pressure at point A, Pa is equal to P naught, that is directly contact with the atmosphere. Atmospheric pressure means pressure at the surface of the water. The pressure at the point B at the bottom of the vessel will be pressure at A plus pressure due to the liquid, P naught plus rho GH. Here gauge pressure is rho GH, excess pressure above the atmospheric pressure, but absolute pressure is P naught plus rho GH. We can also calculate the variation of pressure with respect to depth. Here pressure at depth h from liquid surface, P is equal to P naught plus rho GH. We can calculate the differentiation of P with respect to h. dP upon dH will be, that is constant, will be 0, and h differentiation of h will be equal to 1, that will be rho into g. This is called the pressure gradient also. Positive sign shows that pressure increases with the depth from the surface of the liquid. Now when we are going to solve the problems, we should keep the following facts in mind. Whenever we will solve the problem, we will keep these concepts in mind. Suppose the same container, cross-sectional area A, density rho, atmospheric pressure P naught, and filled with the depth h. If in problem it is mentioned that an open container, means we have to take atmospheric pressure into account, and the pressure on the just surface of the liquid will be, that is contact with the atmosphere, will be equal to P naught. Hence the pressure at the bottom will be P naught. That will also P naught will transmitted to here also P naught, P naught, P naught, and the pressure due to this liquid will be rho GH. So the pressure at the bottom of the vessel will be P equal to P naught plus rho GH. Second situation, it is mentioned in the question that container is closed. It has also a meaning. Container is closed means the surface of the liquid has no contact with the atmosphere. Means here we have not to take the atmospheric pressure into the account. So the pressure at the bottom of the vessel will be only rho GH. The third situation is, consider, it has been mentioned that a piston kept on the surface of the liquid and an external force F is applied as shown in figure this. So the pressure at the point on the fluid surface, that below the piston, just below the piston, that will be Px. Suppose that point is x, Px will be force upon cross sectional area. Py will be at the bottom pressure that is transmitted due to the external force, that will be transmitted till the bottom. The Py will be force upon area, that Px plus rho GH due to the liquid of height h. Here we should note that if nothing mentioned about the mass of the piston, then we should consider it as massless piston. Now suppose no external force is applied and the piston is massless, then here external force is not applied and also piston is massless, but it is free to move, means it is direct contact with the atmosphere, and the atmospheric pressure will work on the piston, and that pressure will be transmitted to the surface of the liquid, and that will be transmitted till the bottom of the liquid. Now suppose no external force applied and the piston is massless, then Px will be P naught, means that here the pressure will be equal to atmospheric pressure. So the Py will be P naught plus rho GH. Here we should be very clear that piston is free to move, so the pressure on it is atmospheric pressure, and we should not be confused with the closed container case. Here if it is piston is kept here and that is free to move, then it should not be confused with the closed container, right? Now consider the another situation, the same piston of mass m. Suppose it is mentioned in the question that the piston is of mass m, but there is no external force is applied and no atmospheric pressure will be taken into account. The pressure on the surface will be due to the weight of the piston only. So pressure on the point x will be m into g, mass of the piston, upon cross-sectional area of the piston, that is also the container. The cross-sectional area of the piston and container will be equal. So Py will be mg plus a plus rho gh at the bottom of the container. That three different type of the situation we have discussed here. We will solve a problem here. We have studied all the concept of the pressure. So there is a dam of bit B and the water level is of height h. So find the force exerted by a liquid of density rho on the dam of width B as shown in figure. The atmospheric pressure is P naught. Here we will take the atmospheric pressure into the account because that is the open container. This is the situation like the open container. Atmospheric pressure work on the surface of the liquid, and that pressure will be constant throughout the height. Suppose a strip of width dy at a distance y is taken for the dam. The differential area will be B into dy and total pressure at this distance will be from the surface of the liquid atmospheric pressure plus rho g y. So df will be P naught plus rho g y B dy. Integrate this force from the height 0 to h. Y will vary from 0 to h. 0 to h. Calculate this integration. It will come f is equal to P naught bh plus half rho g bh square. As the same we have calculated here. This half rho g h square b. Here we have not taken the atmospheric pressure into account because the container is closed. So the force due to atmospheric pressure is 0 here. But in this situation force due to atmospheric pressure is rho naught bh. So here we can also calculate the force separately and add the force due to the liquid height and force due to the atmospheric pressure. Force due to atmospheric pressure will be, what is the area of the dam side? B into h, and pressure is P naught, that is working perpendicular. And the pressure is P naught, that is working on the side throughout the liquid height. So the force will be P naught into B into h. Here see P naught into B into h, and due to the liquid height the force is half rho g h square b, that I have calculated. We added this both force, we found this force that we have calculated from this integration also. This force has two parts as I have already discussed. Force due to atmospheric pressure and force due to depth, that is varying of the liquid. Now we will consider the variation of pressure along horizontal in acceleration, accelerating fluids. Suppose there is a container filled with liquid that is moving right side with a constant acceleration a naught. The shape of the liquid will become like this. The shaded element, we have taken elemental cylindrical. We have taken the cylindrical element here. we'll we will take the mass. We will draw the free body diagram of this elemental cylinder. Here the force is working due to the pressure P1 in the right direction. Here the force will work in the left direction, F1, F2. This body is moving with acceleration A0. What will the mass of this cylindrical part? Cross-sectional area we have taken, suppose, is delta A. So delta A into length will be the volume multiplied by the density will be the mass. So F1 minus F2 is equal to mass into acceleration. F1 will be P1 into delta A, or P1 will be, that is the open container. So here will be the atmospheric pressure also. A pressure on the height H1, P0 plus rho g H1. F2 will be P2 delta A. Here is also the atmospheric pressure and the pressure due to height H2, rho g H2. Mass of the body will be delta A into L, volume into density. So we will put these values. P1 delta A minus P2 delta is equal to delta A L rho A0. From this we got H1 minus H2 upon L is equal to A0 into G. Also from this figure, that length is L and that height will be H1 minus H2. Tan theta will be H1 minus H2 upon L. H1 minus H2 upon L, tan theta. We will equate these two equations. Tan theta will be A0 upon G. Theta is equal to tan inverse A0 upon G. If the container is completely filled, second situation. Here we will now discuss the second situation. If the container is completely filled and the container is closed also. So here we will not take the atmospheric pressure. The pressure varies vertically as well as horizontally. When there are no acceleration, so the pressure is varying only vertically, but here is a horizontal acceleration in the container. So the pressure will also be vary horizontally in the liquid. We have already derived this equation dp upon dy is equal to rho g. That is we are moving from this point to the point O. The pressure will vary dp upon dy is equal to rho into g. Means pressure will increase. Suppose we are moving from the bottom to the surface, means so the dp upon dy will be minus rho g. Minus sign shows that when we are going from bottom to the surface, the pressure is decreasing. We will now consider a horizontal situation. How the pressure is varying horizontally. So here from the free body diagram, F1 minus F2 is equal to mass into acceleration. So we are going to calculate the pressure variation from O to X, means that is B, that is point C. The pressure at C minus pressure at B. So we will discuss the variation of pressure at C minus pressure at B. So F2 minus F1 is equal to, change the sign, mass into minus m into acceleration. So P2 delta A minus P1 delta L will be delta L rho A naught. So P2 minus P1 upon L will be minus rho A naught. That is the pressure difference, that is the length difference. So it is just like dP upon dx, means pressure change in the x direction upon, so it can be written as dP upon dx, pressure change while moving in the x direction. So that will be minus rho A naught. Minus sign shows that pressure is decreasing while moving in the direction of the acceleration A naught. Here, if acceleration A naught is 0, if A naught is equal to 0, then dP upon dx is equal to 0. That is also satisfying the concept that we have already discussed, that in the fluid, on the every point horizontally, the pressure will be same. If the height from the surface of the liquid is same, then on all the points that lies in this horizontal line, the pressure will be same on all the points. So from this equation also, that is clear that if the container is not moving with acceleration A, the pressure will not vary horizontally, and the pressure will be equal, and the pressure will be equal at all the points that is horizontally located at the same depth from the liquid surface. Okay, so we have learned all the concepts. I am telling all the concepts means all the concepts that is related to pressure in the fluid mechanics. We should be able to solve all the problems related to pressure. Thank you.